Welcome to the third and final installment of All About Lenses. I'm your host, Mr. Smith. Hopefully you have finished your converging lens practice problems, number 1 and 2, and you're ready to move on to diverging lenses. So that's what we're going to work on here. So similar to our last setup, except we're just swapping our converging lens for a diverging lens or a concave lens. So you notice the lens here is caved in the middle and thickest on the edges. Okay, so a diverging lens is going to spread out the light when it passes through. It's going to look like it's coming from the focal point. Instead of going to the focal point, it's going to spread out like it's coming from the focal point. So in this example, we got a 3-meter tall flower. So if we're writing down our givens, that's going to be our HO. Our HO is 3 meters because that's the height of the flower. It's located 10 meters away from the diverging lens. So 10 meters is going to be our object distance. And the diverging lens has a focal length of -4 meters. So remember, that's a key clue there. If it doesn't tell you in the problem what kind of lens it is, if you see a negative focal length, you automatically know it's a diverging or a concave lens. Okay, so just like last time, we're going to find the image distance, the magnification of the image, and the height of the image. Then we'll use that information to classify the properties of our image. Okay, so we're looking for di, our big M, and our high. So let's get to it. So in order to find our DI, we're going to use our same lens equation from before, 1 over F equals 1 over di plus 1 over dou. All right, so we plug in our F, -4, our dou is 10. I'm going to use our inverse function here on our calculator to solve it. So in your calculator, you're going to plug in parentheses -4. Make sure you do the negative sign and not the minus sign. So -4 inverse minus 10 inverse, close your parentheses, then hit the inverse button again. If you do that correctly, you should get an answer of -2.86 meters. Okay, so we got a negative image distance. Next step, we got to solve for M, the magnification. Remember, we got two magnification equations, high over HO or negative di over dou. So we don't have the high yet, so we got to use our negative di over dou equation. A little bit tricky here. We got a negative sign in the equation, but we also got a negative sign for our DI. So think back to algebra. A negative of a negative is just going to make a positive, okay? So you got to make sure and plug in that negative from the -2.86 and the negative that's in the equation, because they're going to cancel out, okay? So a negative of a negative makes a positive divided by 10. So our magnification is positive 0.286. You don't have to write the plus sign. I just wrote it there to illustrate that two negatives make a positive when you multiply them together. All right, last thing we need is to find the image height. So solving for high, we're going to use our other magnification equation, high over HO. Okay, so now we got our magnification from part 2. We know the height of the object is 3 meters, so we just got to plug that in. Easy math there. We just got to multiply. There's no inverse or anything like that. Multiply across 3 times 0.286 gives us an image height of 0.858 meters. Remember, when you're putting answers into eClass, I would always include at least 2 decimals, but 3 might be a better choice. Okay, so I would definitely not round this to 0.9 because eClass is going to calculate the answer. It's going to include every decimal point that's on there in its answer. So if you round and don't keep enough decimals, it might mark it wrong because it's going to give you like a 2 or 3% buffer above or below the exact answer. So as long as your rounding is within there, you're okay. But if you rounded this to 0.9, it would actually mark it wrong. So I would at least keep 0.86 at a minimum, but 0.858 would be a better answer there. So to classify our image, we got to look at our answers to these 3 problems. Okay, to figure out if it's real or virtual, we got to look at our DI, right? Since our DI is negative, that means we have a virtual image. So it's going to appear on the same side of the lens as the object, and we're not going to be able to see it on a screen. All right, in order to figure out if it's upright or inverted, we got 2 options. First thing we can look at is our M. Since our M is positive, that means our image is going to be upright. If M was negative, it's inverted. Other thing we can look at is our HI. Our high is positive, so that means our image is also going to be upright. Okay, so M and high are always going to have the same sign. Okay, because remember, the height of the object is never going to be negative. You're never going to start with an upside down object. But So your magnification and your high are both positive, so that means you got an upright image. Last thing we got to figure out if it's magnified or reduced. Once again, we can look at M or high. Okay, if we look at M, we know that number is a decimal, it's less than 1. So that means it's going to be smaller than the original, right? It'll be like 28.6% of the original object size. The other way we can look at it is look at our high. The height of the image is 0.858, which is less than the object height of 3 meters, okay? So since high is smaller than ho, that means we have a reduced image. So we can take these classifications and we can plug them into the chart we've been working on, okay? Before we do that, let me show you what this image will actually look like. Remember, I mentioned you're going to see this in the lab later this week. So we got our object on the left side, that's the big sunflower, okay? Our image is the small sunflower there. It's a virtual image because it's on the left side of the lens, just like the object is, okay? It's an upright image because the top of the sunflower image is towards the top of the screen, just like the original sunflower, okay? The stem is at the bottom. And it's reduced because it's shorter than the original object, okay? The original object is much bigger than the image you see. So we get a virtual, upright, reduced image. So we plug that into the chart. We're down at the bottom for the diverging or concave lens. Remember, it's got a negative focal length. We plugged that in at the very beginning of the first lesson. So we started with an object that was far away, way past 2f. Okay, our image ended up closer than the focal point, a little bit different than the convex lens. Okay, our M here was positive because we had an upright image, but it was still less than 1. So it's still a reduced image, but it's upright in this case. So if we look at our image classification, it's virtual, upright, and reduced. Contrast that to our convex lens that's far away, had a real inverted reduced image. So both of them are reduced because they're far away, but this one is virtual and upright for a concave lens. So in your notes, you got 2 more practice problems for those 2 other distances. So go ahead and do those, classify those images. And once you've finished all 4 practice problems, go on to eClass and enter those into the quiz. Thanks for tuning in. Make sure and ask your teachers if you have any questions, and stay safe out there.